in sort of opinionated, more important things. So let me just do this real quick. And then I'll update the annotated PDFs later. So before we dive into it, how do you guys feel about the paper, Ali and Rosalind?
It should have a few interesting parts. Actually, the only part I find interesting is the different update schemes, or should I say modes, probably, auxiliary or joint. But beside that, I think the core of the PPO stays unchanged. So
Yes, I think so too. What about you, Ali?
Yeah, I wonder how much the sharing of the representations and the policy and value impacts. They have this note here that they notice that it does vary across environments, so just wondering how much it varies actually.
Yeah, so I think somewhere they mentioned that in pixel domains, sharing features or sharing representations might be important, but in continuous action domains like Mojuko, it might not be as important. So definitely interesting topics to look into today.
Interesting.
All right, so today we don't have many people joining, so feel free to interrupt me if there's anything you want to add, or if there's any questions, just kind of a discussion style, and I'll just kind of sort of capture things that I think are very interesting in the paper and try to go through it. I think the abstract is very well written, so I just kind of copy and pasted it. So it basically says in prior methods, we usually have to choose between a shared network or separate networks to represent the policy and a value function. Using separate networks avoid interferences between objectives, while a shared network allows useful features to be shared. PBG is able to achieve the best of both worlds by splitting optimization in two phases. One that advances training and the one distills features. PBG also enables value function to be more aggressively optimized with a higher level of support reuse. So what that means is that this is our code. On the left, you see the neural network architecture for playing Atari, and on the right, you see the neural network architecture for playing for Mojuko. Right, so I can make this to full screen. Can you guys see? Can you guys read the code over here?
Yeah, that's better.
yes.
Okay. So in PPO Atari, you see basically you have this shared network, and then you see in the bottom you have a self-actor and the self-critic, and those are basically what they call the self-actor is a policy head, and the self-critic is a value function head. So they share this common network that is over here. However, in Mojuko, you see the critics and the actors or the policy are shared. Well, they have completely different neural networks, even though they have similar sizes, but they're off different parameters. And when you do the optimizations, they're done differently. So if you're optimizing against the value function, you're not really impacting any parameters in the critics. Basically, if you're optimizing against the value function, you're not impacting the parameters of the policy. So that's kind of what they're talking about. Does that make sense?
Yes. A quick question.
Yeah.
I remember in our previous implementation of PPO, I believe the one on the left was use separate networks.
Yes.
So is but also in your PPO Atari, you already have this kind of policy and actor at, in other words, the shared networks. So
Yes.
In what paper was this actually introduced?
So
maybe what implementation?
So when we implement for the PPO, this is actually the default behavior by the PPO. So by default, PPO from the implementation of PPO from OpenAI baselines uses a shared neural network architecture for Atari games and uses separate neural network. Yeah.
Okay. Actually, I quickly tried both, and well, they seem to work well enough on Atari, but I'm not sure of the difference yet. Maybe one is faster than the other. Okay, well,
Yeah.
we'll see later, I guess.
Yeah, so this is basically the topic of this paper. It's saying, so when you do the actual training, right, especially if you have a large neural network and you have a lot of convolutional layers like Atari, then training with shared architecture is really fast, versus if you were to do the separate architecture, which will be a little slower. But yeah, so that's sort of one obvious benefits, and we'll talk more about it. So obviously, if you're sharing the architecture, the feature trained by the both objective can be used to better optimize the other. So they kind of work together. And as I mentioned earlier, I think they did mention it. They probably mentioned it somewhere that it's much faster to just train with one single neural network instead of having two. If you're having two over here, the critics will look as large as this, and the actor will look as large as this, which is undesirable. So the disadvantage of sharing with the neural network is that this is also from the paper. It's not clear how to appropriately balance the competing objective of the policy and value function. So in other words, when you optimize the objective versus the shared neural network architecture, if you're optimizing let's say the values objective, the parameters that produces the values are also the parameters that produces the policy. Therefore, when you optimize against the values, you're also modifying the parameters of the policy as well. So that's what they're sort of talking about the competing objectives, and one could mess up the other. And the second disadvantage is that use a shared network all but requires the policy and value function objective to be trained with the same data and consequently the same level of sample reuse. This is an artificial and undesirable restrictions. So, Rosalind, if you remember the PPO implementation from OpenAI baselines, it can basically split the optimization of the value function and the policy into two different phases, and you can choose sort of update iteration for the policy and for the value function. But yeah.
Yeah, the spin-up one, right?
Yeah, the spin-up one, yeah. In spin-up one you can, but in OpenAI baselines you couldn't.
Oh, okay.
Yeah, so in OpenAI baselines you always use the same number of update iterations for both the policy and the value function. So that's kind of the problem that they're talking about. And another related paper on this topic is what matters in policy reinforcement learning, a large-scale empirical study. And so I've linked the paper over here, but it's basically saying they have done some experiments with whether to separate the value and the policy network, which is related to this topic. And they basically say separate value and policy network appears to lead better performance on 4 out of 5 environments, which is pretty big, but it's also only just 5 environments.
And were these environments with pixel inputs, or were these classical? Were these environments with pixel inputs, or were these like classical control Majoko environments?
Yes, these are classical control Majoko environments. So these are not Atari environments.
Okay.
Yeah, so we have no idea whether this conclusion will apply to the Atari environments. But it sounds like in the PPG paper, separating the policy will lead to worse performance in the pixel environments. But these are, sort of guesses that have anecdotal evidences that might not be true in general. So basically, PPG works like this. It sort of it sort of gets the best of both worlds of sharing architecture and training networks separately. So they basically have this policy phase, That, from my understanding, is basically training the PPO. So one thing to also notice, this doesn't. Yeah, you have to look at the next slides. So in let's say in our PPO Atari, you basically have this. So PPO Atari, this neural network architecture, corresponds to this. So basically, they have two sort of value function heads. This is the value function head of the neural network, sort of like the PPO Atari, but this is a completely separate value function network. So over here in the policy phase, when they're doing the value function update, they're using this totally new, totally different value network that is separate, that uses a separate network. But other than that, everything in the policy phase is exactly the same as PPO. And then after that, there is this auxiliary phase that is not the structure of PPO. In the auxiliary phase, they're basically optimizing this joint objective. And I didn't highlight over here, but this is the joint objective, and auxiliary loss is basically the value head loss versus the value target loss. Minimize this mean square distance between the value head of the policy and the value target calculated by the general GAE. So this is used as an auxiliary loss. And you also have this behavior cloning coefficient times this KL divergence between the old policy and the new policy. So so this sentence, I think is really important to understand what is going on. So it says, that is, we optimize it's this sentence. At present, we simply use the value function as auxiliary objective, thereby sharing features between the policy and the value function while minimizing distortion to the policy. Minimizing distortion to the policy means they're trying to minimize the KL divergence between the pi ode and the new pi, which means so from my understanding is that the joint loss is basically trying to reuse the value function, trying to retrain the value function as many times as it can while still remain the same amount of policy outputs or distributions. Does that make sense?
How is that KL term similar to the policy ratio RT in the loss, the clip loss for the general clip surrogate objective?
That's a good question. I don't know, but that's the one that they choose to use. So, yeah, I don't know. That's a good question. I think in PPL originally, they also have this similar idea where they have this kind of adaptive KL penalty, which is also kind of talked about later in this paper. But I guess this could also be some sort of a clipped coefficient, clipped objective over here as well. But I don't know.
Yeah, it seems like the trust region objective or the clip objective that we've seen before.
Sorry. Could you say that one more time?
It seems like it's similar to the penalty that's provided in TRPO for the trust regions or for PPO for the policy ratio. I'm not sure if it's different somehow.
I think in PPL, in TRPL, they're basically saying they're trying to maximize the ratio while maintaining the KL distance between the old policy and the new policy to. They don't want the new policy to be too far away from the old policy. So I think that's a little different. Another thing to notice is that, I don't know. Let me take a look real quick. I think it's a little bit different from the adaptive KL. Yeah, I think it's very. Never mind. It's very similar, right? This is also minus beta times the KL of the old policy and the new policy. Yeah, so I would say this is actually kind of like the adaptive KL loss in the auxiliary loss of PPG. Right. Yeah, that's interesting. Thanks for bringing it up. All right, let's continue going. And this is where everything sort of comes together, right? And it's basically saying I am going to run PPO for a certain number of policy phase. And in each policy phase, I am going to update my policy and a value function separately. And then I'm going to add all of these related data into some sort of buffer. And then I would start doing the auxiliary phase. And then optimize the join objective. And then also do some additional optimization on the value function as well. Even though, right, so the joins loss, it optimizes the policy head, right? And the loss of value optimizes the value network, which is a separate network from the policy network. So auxiliary phase is kind of doing something different. So from my understanding, when you actually do this, what that means is that, so if you're maybe a little bit familiar with our source code for PPO, we basically have for update to, you know, however, I don't know, 5,000, 6,000 updates, that is for 10 million time steps or whatever. And then you do this policy updates or whatnot. I think it's basically saying, I'm going to do the policy updates for every 5 or 7 updates. If updates modular 7 equals 0, then I'm going to start the auxiliary phase. So that's what the periodic auxiliary phase is. I think that's how it works. Okay, yeah, any questions or things to discuss at this point? Okay, I'll keep moving on. And basically, the results are very different, are very interesting. So the first is the comparison between PPO. This is something like a note. So the general emphasis is that we have noticed that the importance of representation sharing between the policy and the value function does seem to vary between environments. So while it is critical to share parameters between policy and value function in proxy environments, this is often unnecessary in environments with lower dimensional input space. So which would be something like the major context. We conjecture that high-dimensional input space in proxy contribute to the importance of sharing parameters between policy and value function. We therefore believe it is in environments such as these, particularly those with vision-based observation, that UVGB is most likely to outperform under similar algorithms. Okay, yeah, so that's just a note. We're just kind of saying, yes, the conclusion or the results from the paper that we linked in our related work might be true, but that's might be true only in the continuous actions domains, but not in vision-based domains. And here, from my perspective, this is where things gets interesting. So it's saying the policy sample reuse. So it shows this graph. So remember, look at this algorithm, and we look at this ePi, right? This is a policy FX. And in PPL, the sort of corresponding hyperparameters would be this update iteration networks, which is 4. So that's what for, or that's what this epi is. And it's basically saying by keeping all the other parameters the same, the higher you update with the higher you set the update iteration for the policy, the worse the performance gets. Which is very interesting, right? In PPO, we always think that the reason that the PPO is performing better than B2C is because it's able to reuse the policy updates. It's able to reuse the previous samples to do another policy updates. But based on the experiment shown over here, no, it's not. And basically, they're going to show that it is actually the value sample reuse that's really increasing the performance, but not the policy sample reuse. So let's look at a conclusion from the sample reuse. It says, as we can see, training with a single policy epoch is almost always optimal or near optimal in PPG. This suggests PPO baselines benefit greater sample reuse only because of the extra epochs offer additional value function training.
The fact that it's deteriorating, so like the light blue lines are significantly lower. What does that mean in terms of what the policy module has learned? Is like overfitting, or is it what's the underlying root problem there?
I really don't know. I think that's something probably very fundamental with policy gradient, which with that kind of theory, I am not very equipped to provide answers for. But I think it has something to do with the way you do policy updates. Specifically, in PPL, you have this split objective, but it's in actuality you should update, I guess, with some sort of all policy gradient. They sort of clipped it, but they also kind of do things a little differently. So I don't know. So in other words, I don't know what's the best answers for that. But they're basically saying, in other words, I guess there's also a lot of research to be done on the policy sample reuse. Can we improve policy sample reuse to further increase the sample efficiency?
Right. Okay. Thank you.
Yeah, that's a good question.
Just an intuition, but when it comes to the policy network update itself, I remember in some of our experiments, the more we do it, the higher the divergence, which is actually what breaks PPO itself.
Yes.
Mm-hmm.
Yeah, go ahead.
But we also have seen that when it comes to the value, we could actually update as much as we wanted, since we did not have the KLE stop was only applied to the policy. So at least in the PPO specific case, too many updates is what causes the policy divergence. I think it was something like collapse or catastrophic unlearning, maybe.
Yeah, catastrophic. Yeah. So what Rosin is talking about is a paper that we co-authored, submitted to NERIS, but unfortunately they rejected.
Oh, dang.
Yeah, it's okay. But it's a learning experience for both of us.
Right. Yeah, it's so cool you get to collaborate on. Hopefully you can resubmit to another one with some improvements, maybe.
Yeah, thanks. And I don't know how we're going to modify the paper, especially with the things like PPG coming out. I don't know. It feels like I don't know. That's something that we can discuss more. But yeah, things
By the way,
yeah, go ahead.
When they analyze what the update reuse, what was the specific term? Could you bring the slide back, please?
Yeah. Which one?
Yes, the policy sample reuse. What was the other reference? Was it also another PPO or
the policy
some other
sample reuse? Based on my understanding, is basically the update iterations per epoch
of the policy network.
Yes, of the policy
itself,
network.
right?
Yes.
And
So
what did they compare it with? Maybe some off-policy methods? I do not exactly remember that part.
I mean,
What are
I
that's,
you
see
talking about?
that graph
the
just
PPO.
shows.
Oh yes, the graph at page 12.
In the paper, page 12?
No, the presentation slide 12.
Okay, yeah.
So that's just, I think,
Us.
e pi is the number of epochs for that policy update, right? So
Yeah, for the policy reuse.
The lower, the better.
Yes, basically. Basically, one is the best.
it's just one epoch, it's just one pass through the data, I guess.
So for me, this is the most interesting results. Like if you read the algorithm, it doesn't seem. If you read the literature, the first 2 pages, it's like auxiliary based grades. But it's really when you read the policy sample reuse, then you have some questions about PPO. You realize its performance is probably, its policy sample reuse is probably not as good as it's.
And learning curves, like in the Pacific learning curves, are also interesting. Like the chaser environment, for some reason, is significantly different for less epochs, but then like maze and minor aren't so different.
Oh, I see. Oh yeah, that's interesting. Yeah, in some domains, there's almost no difference, right?
Right. It's never the case, I guess, that it is better to do more epochs, though.
Yeah.
So.
And keep in mind that if you're doing one epoch for policy sample reuse, then it is basically the objective for A2C or A2C.
Right. Okay.
Right, because at that point, if you're clipping the objective, everything is going to be 1. There's nothing to be clipped from. So specifically, if we do a really quick demo, this is what happens. So you just kind of run things and you see this ratio. The ratio for the first epoch, policy ratio, is always going to be 1. But then if you do the updates, and then you calculate the ratio again, you're going to find the ratio is a little bit different. And that's when the PPO's clipped objective kicks in to sort of, I don't know, do its magic and prevent things from blowing up. But if you're doing just one epoch, it's literally the same as A2C's objective. So they're basically saying you should train more on your value function, but do the A2C's objective.
Interesting.
Yeah, I think it's very interesting as well. So on the next slides, they're talking about the sample reuse. And it's interesting that if you look at the pseudocode, right, they're saying don't do the value function. They're saying don't do the value function reuse too much over here, but do the value function reuse, sample reuse over here, which I thought was a pretty interesting point. They said, we find training with additional auxiliary epochs is generally beneficial with performance taping off. So this is a performance of auxiliary phase, by the way. So basically, the higher auxiliary phase, the better the performance. And if you read the paper, you go to the end, and you find their hyperparameters, you'll find their policy epoch and the value function epoch is 1, which means for the value function sample reuse, it only happens in the auxiliary phase. So which means over here, it's just 1. For epoch equal to 1, do this. For epoch equal to 1, do this. For epoch equal to 6 or 12, do these. That's where the value function gets reused. So So that's kind of their results. And they have some interesting observations. They have some, I think, interesting suggestions or intuitive arguments. They say, first, due to the optimization of our joint, we may expect better trained features to be shared with a policy, which are done in the auxiliary phase. And the second, due to the optimization of L value, we may expect to train a more accurate value function, thereby reducing the variance of the policy gradient in future policy updates, which is kind of similar to the, I don't know, in a way like TD3, because they're also basically doing more value function updates than policy updates.
Interesting observation. Interesting observation indeed.
Yeah, definitely. They have, yeah. I think it makes a lot of sense over here. And then it is this auxiliary phase frequency, which are sort of controlled by this MPI. So which is this parameter. So that means how many iterations or data do you want to collect before doing the auxiliary phase? Which means if you're doing this, if you set this MPI to be 32, it means you're not going to do the auxiliary phase very often. If you set this MPI to be 16, if you set the MPI to be 2, you're going to do the auxiliary phase very frequently. So their conclusion is basically don't do auxiliary phase too frequently. I think I forgot to copy the slides, but yeah, it is clear the performance suffers when we perform auxiliary phase too frequently. We conjecture each auxiliary phase interferes with the policy optimization, and that performing frequent auxiliary phases exacerbate these effects. Okay. So yeah, that's also an interesting observation. Interesting empirical fact to know, I guess. And then this is the difference between the KL penalty objective versus clipping. So that's just a PPO thing, and they basically, I think, find no performance difference. I think maybe with the PPG with clipping, it's a little bit more unstable. Yeah, it's really inconclusive, I would say. And they also have this sort of a hacky single network PPG, where they suggest, because PPG has a separate network for the policy and the value function, it comes with increased memory footprints because you need to have twice as many parameters as PPO. So they can recover this cost by using a single network that appropriately detaches the value function gradient. So I think that's
What does that mean? They just freeze all the gradients for the value function during the policy update phase?
Probably just the CNN part.
I see.
Which part are you talking about? Oh, are you talking about the sentence during the policy phase we detach the value function gradient at the last layer shared by the policy and value heads?
Yes, what does it mean? What does that detachment mean? They just freeze everything prior to the head and the value function when they do the policy update?
So I'm pretty sure this is what it means. So let's say we do this update, right? Just kind of a quick demo. If I do this update and I do this, this is just how you do the updates in PyTorch. You get a loss and then you backpropagate the loss.
Yep.
And then you go see the agent parameters, which are a bunch of them. But since they share parameters, you can say agent.actor dot weight. And then you can see their gradient as well. So I think what it's basically saying by detaching is basically set the gradient dot grad equal to 0 or something like that. So if they're optimizing the value function, they freeze the weight for the actor or vice versa, so that one is not affecting the other.
So,
or sorry, it might
the
be
critic, I guess.
Sorry, what?
I guess in this case, for the value function, it'd be the critic, right?
Yeah. So I think they're actually not talking about this layer, but rather this layer. So if you freeze the gradient for this layer during the actor update or the critic updates, I think that's what the single network. It's kind of a hacky thing, but apparently it works very well. At least it improves the sample efficiency. So this is kind of their result. PPO is here, and if you're using this single network, is a little bit more unstable, but it performs just as well, basically. But it's also interesting, right? If you look at all of the environments, they sort of catch up with the performance. Never mind. Yeah, it's really inconclusive. So yeah,
it makes sense.
Sorry, what?
I think it makes sense.
Yeah. So I think it's overall, I think it's a very interesting paper, and for us, I think it'll be interesting to integrate. So another thing I want to quickly mention is that for their CNN, for the convolutional neural network, this is kind of the implementation detail that I just kind of started digging into it. But they started using this Impala convolutional neural network, which is different from the sort of basic convolutional neural network that was used by DQN for the from DeepMind. So that's also another thing to take into consideration when you try to do the reproduction, doing implementation for the production environments. Sorry, for PVG. So another thing is that, so I dig into the implementation a little bit, just kind of had a little bit of experiments. And since they're not using frame stack, you don't need all of the Atari preprocessing. You really just need the image to PyTorch, and maybe, so I'm using the clip rewards environment, but maybe you should be using the reward normalization thing, the running reward return normalization that was used in their paper. So they mention it somewhere. Where is it? Yeah, so they say we avoid this concern by normalizing rewards so that discounted returns have approximately univariance. So that's also code level optimization that when we do implementation we should take into account. And when I started doing implementation, basically everything kind of stays the same except deleting a couple stuff, and also you need to change the neural network architecture a little bit. Before in PBO Atari, I think this when you flatten the observation, this is much higher. Let me see how much it is. So in Atari, because the pixel is 84 by 84, I think, but over here in production it's 64 by 64. So the linear layer also has to be adjusted accordingly. And the way you do that is you get the next observation, which would have the shape that looks like this, which is a 64 by 64 3 channels RGB channels observation from 8 environments. And what you have to do is you do this. You sort of copy this. And you say G equal to this dot to device. Well, you put 3 channels over here. And then you say G next observation and then check its shape. So this is so from a 64 to 64 image with 3 channels, it gets convoluted with the channels in stride into a 4x4 with 64 channel observation, and then you need to basically 64 times 64, which equals 1024, and put it over here. So that's kind of how that number is calculated. And yeah, if you get that, it basically works. I'll be committing this file so that if you guys want, there's going to be a reference to sort of how to get started. But yeah. What do you guys think?
Just one other thing, I was reading through the last part of this. So in this one, I guess, does also have replay buffer for the auxiliary learning. Mm-hmm. So it's not really off policy, but you still use like previously collected data for updating.
Yeah, I don't think it's off policy. It's really just yeah, there's nothing off policy. I don't know. It's definitely not like DQN. That is not a replay buffer that you sample from, right? It is just like an array that you append a lot of things.
Yeah, that
can bring back the algorithm slide.
Yeah.
I believe regarding the policy itself, it's on policy because by default they suggest to use only one for ePi and EV, right?
Mm-hmm.
And then, well, there's also, since it's PPO, it uses a relatively small buffer. So we use the same small data set. It's B, right? Wait. Because in the auxiliary phase, they also say use all the data in B, but just update the value a lot more.
Mm-hmm, mm-hmm.
Just the value.
Yeah, so I guess that would be off policy, but it's definitely not like the replay buffer that you sample from and add it to.
Since it's the value that is updated mostly, do we even need to mention the term off policy?
I don't.
Is it off policy?
Yeah, I don't think the off policy is really.
It does not really matter for the value, at least. I think.
Yeah, I don't know. It does not seem to be a very appropriate term.
No, actually, since in loss joint there is indeed some term related to the policy, so yes, it is off policy in a certain sense.
So that if you look at the auxiliary loss, so when you're talking about off policy updates, it's usually you need to adjust the important sampling. But in the auxiliary loss over here, it's just really saying I want to minimize the policy change. So that's
the
it.
Policy change. Okay.
Yeah. So that is just like an additional penalty term. I wouldn't really call it a policy update.
Interesting. Also, okay. Since we are here, if I understand correctly, the theta pi and theta v, two different networks, So at first, I thought they share at least the CNN pre-processing part, but it
No.
seems both of those are completely different.
Yes.
And the part where they share it is actually in their single PPO network experiment. But they
Yes,
say
I
they
think.
detach. They share the CNN, but they detach when they update the theta V part, basically.
Yeah, I think so. They detach some part of the gradient.
Ah, I see. I messed up a little bit.
Yeah. I was sometimes confused about it as well. Like specifically over here, they say they use this M pi to control the frequency of auxiliary phase. I was like, what does that mean? Yeah, I can look at the and I understand what this means. Because if you look at the code, it's kind of saying basically they train the PPO and then the auxiliary phase comes. So specifically, let's see that code. Okay, hold on. Is that appropriate codes? You go to policy gradient and you go to PDP. You go over here somewhere. So it's basically first, and then you do. So then it starts to make more sense for me why the auxiliary time parameter that controls the frequency of the auxiliary methods.
Yeah, it's kind of tricky, but there seems to be like four loop, at least not four loop, but two loops inside each other's. Wait.
Also the way they write it. Yeah. It's also the way they write their source code. In their source code, they have a lot of NPIs to, I suppose, improve performance. Obviously, that's great, but it's a little harder to understand.
Also, I see that in a PPO Atari, which I started up with, it seems that there is the vectorized environment that are used. So how do you think it will change the policy?
It shouldn't make any difference. So
Oh,
if you look at
okay.
okay,
Since we have parallel environments, in the end, once everything is sampled, is it as a single sequence in buffer?
like, do you update? Do you get a lot of rollouts and then you update them together?
Is all the data together in the PPO buffer?
Oh, so if you look at the code for Go, right? So basically, we have some observation actions, a lot. So are basically using the policy phase. So for the auxiliary phase, of moves together. Does that make sense? Yeah, so this is for policy phase 1, policy phase 2, policy phase 3. And after the buffer that they talked about in the pseudocode should have these observation, at least some of them from policy phase 1, policy phase 2, policy phase 3. Does that make sense? That's that is.
Is it only me or the network is quite unstable?
Yeah, especially with Costa's audio, it seems.
Yeah. Choppy.
Oh.
It's choppy.
My bad.
That's better.
Okay, let me try say that again. So basically I'm saying these observations, these will be used for policy phase 1, policy phase 2, policy phase 3. And then in order to update the auxiliary phase, you need these from policy phase 1, policy phase 2, phase 3, and you concatenate them together for the updates in the auxiliary phase, I think.
Yes. Okay.
So it needs to be rewritten in certain ways somehow.
But they also use parallelized environments in their code, right?
Yes, absolutely. So basically, I think when we implement this, everything over here will be the same. So all of these will be the same, except here. You're going to say, in the end,